Did you know that all of the stars you see in the night sky are spinning? In fact, most stars spin fast early in their lifetimes and then slow down as they age. We can leverage this fact to estimate a star's age using its rotation rate. I'm Claytor, a grad student at the University of Hawaii Institute for Astronomy, and in this Aloha Brief, we're going to review a few key points from my recently submitted paper, in which we use rotation-based ages to study chemical evolution in the Milky Way. Age is a fundamental characteristic of stars, but it's one of the most difficult to determine because stars change so little over the course of their lifetimes. There are a number of ways to estimate stellar ages, but in this work we focus on gyrochronology, which uses a star's rotation rate to derive its age. Gyrochronology works best for low-mass main sequence stars. These stars are born spinning fast and spin down as they age. From this relationship, we can map rotation speed, which is relatively easy to determine, onto age. There are also effects from mass and composition, which change the generation of magnetism. But that's it. Knowing the mass, or temperature, composition, and rotation period, gyrochronology can be used to estimate an age. Temperature and composition can be determined from spectroscopy, and we can obtain rotation periods from photometric light curves. Spectra and light curves are natural byproducts of large sky surveys, so there are plenty of data ripe for use in gyrochronology. We studied a set of 900 mostly main sequence stars near the galactic plane. They were observed by both the Kepler Space Telescope and the APOGEE Spectroscopic Survey. We were able to obtain rotation periods for about 500 stars from their Kepler light curves. We used the temperatures, metallicities, and alpha element abundances determined from APOGEE's data reduction pipeline. We obtained ages for these 500 stars using a model-driven form of gyrochronology. The Python code I developed to interpolate, interact with, and sample the stellar models is called Kiauhoku. It's publicly available on my GitHub repository, along with the models themselves. This histogram shows the distribution of ages in our sample. The distribution has a peak around 2 billion years, which is consistent with other studies of stars in the Kepler field. The relative uncertainties on the ages are around 15%. This is better than other age determination methods for low-mass main sequence stars. We used our ages to investigate chemical evolution in the Milky Way. Specifically, we expect the abundances of alpha elements relative to metals to decrease with time. The decrease is steep in the early universe and more shallow during the last 8 billion years. The different slopes are thought to be caused by the dominance of different kinds of supernovae in the two eras. When we plot the alpha to m ratio versus ages for our stars, we see a similar trend. The slope is shallow for young stars and gets steeper for old stars. The recovery of these trends provides an extra important validation for our age estimates. We also see a population of old alpha-poor stars. These have been seen by some other studies. They're evidence that galactic evolution may be more complicated than the two-phase picture we discussed before. We also took a look at some sources of bias within model-based gyrochronology. Using models of stellar spin-down to estimate ages relies on a set of assumptions baked into those models. For example, while some gyrochronology studies have included the effects of metallicity, detailed abundances like alpha elements have been entirely ignored. The spin-down law itself has assumptions as well. We assume that stars have been spinning down long enough to have forgotten their initial rotation periods. This allows us to estimate ages without the need for a star's initial rotation period. We used our models to test the validity of these assumptions. I'll show a quick example here, but for more details you'll need to check out the paper. Let's see how ignoring alpha abundances influences the age estimate. For this, we compared pairs of stars, one of which had a solar alpha abundance, and the other which was alpha enhanced. The two stars in the pair were otherwise identical. Given the same mass, metallicity, and period, but different alpha abundance, we would infer different ages for the two stars because they will have spun down differently over time. We looked at the fractional difference in the inferred age for pairs of stars across a range of temperatures and rotation periods, shown here. For a star like the Sun, which has a temperature of 5800 Kelvin and a rotation period of 25 days, ignoring alpha abundance can bias an age estimate at around the 10% level. For most of the stars in our sample, which are cooler than the Sun, ignoring alpha abundances can cause bias in inferred age as high as 20%. We also ran tests to measure the effects of ignoring metallicity and initial rotation period, but for those, you'll need to read the paper. In this work, we used model-based gyrochronology to estimate ages for 500 stars observed by Kepler and APOGEE. This demonstrates the usefulness of gyrochronology as a tool for estimating ages of stars that are otherwise difficult to date. But users beware, there are several baked-in assumptions and sources of bias that must be accounted for. For more details, check out the paper posted on the archive. To learn more about stellar evolution models and the code I developed to work with them, check out the GitHub repository linked in the description. And finally, to learn more about what we at IfA are doing, check out the YouTube channel or follow us on social media at IfA. I'm Zach Claytor. Thanks for watching. Aloha.